Hi everyone. I recently received a question on the Discord channel about how to find the outside vertical corner edges of a building. So I thought I would do a quick topologicpy tutorial on that and show you how this can be accomplished. So the aim is to find the external vertical corner edges of a building, and this list should not include any intermediate vertical segments of the wall. So any vertical edges like this one that has an interior wall hitting the outside wall, this we should not include. We should only include the corners here. And I will mention at the end some caveats about this process. Obviously, you could refine it a bit more, but this is a simple version of finding those corner edges, and it's a simple building as well. So the first thing we should do is get all the edges of the building. In this case, it's a cell complex. So we can call edges equals topology.edges building, and it will give us all the edges, both horizontal and vertical. So we need to filter out for the vertical ones. So how do we do that? Basically, we start by initializing an empty list called vertical underscore edges, and then we loop through the edges for edge in edges, and we get the direction of each edge. So edge.direction edge. And we check that it is collinear, parallel, or anti-parallel with the up vector. So we have something in topologicpy called vector.up, which points usually in the positive z axis. And we have something called vector.isCollinear that checks whether these two directions are collinear. And it doesn't matter if they are in the same direction or completely opposite direction, like 180 degrees. As long as they are collinear, it will give us a true value. And if that is the case, I save the edge in the list of vertical edges. So as you can see here highlighted in red, these are all your edges. So next, what we do is we get the parent faces of each edge. So how do we accomplish that? We do topology.supertopologies. We give it the edge, we give it the original building, the parent building, which is the cell complex, and we tell it that the topology type that we're interested in is called face. In that case, some edges like this one here will return 3 faces. The one in the middle figure here, this edge, corner edge, will return 2 faces. And if it happens to be an internal edge, like this one here on the right, it will return perhaps 4 faces. So we need to figure out which of these edges are the ones that are corner edges, like this one here, that we need to preserve. So how do we discover that? The way you discover it is you ask these faces for their parent cells. So again, we use the same call, topology.supertopologies. We give it now a face. We're looping through all the faces that have been retrieved. We give it the original building, and we tell it that the topology type that we are interested in right now is cell. So if the length of the parent cell is equal to 1, that's the one we want. So what does this mean? Basically, we ask every face for its cells. So for example, let's take for example this blue wall here with the green check mark. It will return only 1 cell, while the internal wall will return 2 cells, one to the left, one to the right, and so on and so forth for all these ones. We are only interested in the edge whose parent faces all return 1 cell, like for example the one in the middle figure. So this vertical edge returned 2 faces. When we asked those 2 faces for their cells, each one of them returned 1 cell. In this case, of course, the same cell. But they all returned only 1 cell. If that is the case, if that meets the condition, we take that edge and we save it in a final list. I hope that is clear. All the other ones, like for example this internal wall, if you ask for its faces, the faces are each returning 2 cells, so that's obviously not what we want. Now, just a bit of a caveat on this. Obviously, if you had a more complex building and you have, for example, an interior corner, like imagine an L-shaped building and you're looking at the interior corner of it, those corners will return multiple cells if an interior wall happens to hit them. If there is an L-shaped space behind them and there is no interior wall, then they will count as one of the corner cells. That is also true if the building happens to have an edge, a vertical edge on the outside that does not have an interior face hitting it from the inside. It just happens to be a segmentation of the face. That will also count. Technically, obviously, this is not a corner. So in that case, you could take a look at the angle between the two faces that are being returned and check whether this angle is more than a certain minimum, and that would be considered to be a corner. Obviously, these are all refinements to the algorithm that you could add yourself. But in this case, this is a very simple algorithm that returns the corner edges, as you can see here in the final result. I hope you enjoyed this tutorial, and if you have any questions, please don't hesitate to contact me. Thank you.